Welcome back, students. Today we're going to be talking about solving compound inequalities. A compound inequality is an inequality formed by joining inequalities with the word and or the word or. Now, the graph of a compound inequality with the word and is going to be the intersection of those graphs. The reason why it's only going to be the intersection, the place where both of them would have solutions, is because when you use the word and, you have to satisfy both statements. Both have to be true. So think of a number that is greater than 2 and less than 4. So what's the number that's greater than 2 and less than 4? It's going to be 3. You wouldn't say 5 because 5 isn't less than 4, even though it is greater than 2. Both of your inequalities both of the conditions of both inequalities have to be met. So the graph is going to be the intersection where both inequalities are true. So here's another example. If x is greater than or equal to 2, here's the graph. Notice filled in dot because we have or equals to. X is less than 5, empty dot, because not or equals to. Now, if we combine them with the word and, x is greater than or equal to 2 and x is less than 5, we only graph the intersection. Only the intersection, where both of these had a shaded line. We keep the dots from both of them, and it's just that space in between. Now, when we're combining things with the word or, either can be true. Remember that connection of either or. Okay, so the graph of a compound inequality with or is going to be the union of the graphs because, well, either could be true. And so long as one of them is true, we found a solution. So the graph shows numbers that are solutions to either inequality. So when y is less than or equal to -2, here's the graph for that. Y is greater than 1, there's the graph for that. So when I've got y is less than or equal to 2 or y is greater than 1, it's just the combining of the two. It's the union of those two graphs put onto a single number line. Now, one extra thing to notice, if we had used the word and in this final situation, there is no intersection. There is no number that both of these share. So if we used the word and, because there's no intersection, we simply wouldn't have anything on this graph. Okay, now let's talk about writing and graphing them. We've got a number x is greater than -8. Great. And less than or equal to -4. So I've got and that same number less than or equal to -4. In graphing this, I'm going to get a number line. Then I'm going to put a dot on the -8. Notice not filled in because we don't have or equals to. And we needed to be greater than that. So I start having this line that's going in the greater than direction. But I've got a limit to this because it also has to be less than or equal to the -4. So notice, from the filled in dot, we're going in the less than direction. From the empty dot, we're going in the greater than direction. And in that way, we're meeting the conditions of both of our inequalities. Now that's the way it's going to look with and. Next, we got a number is at most 0. Now, at most lends itself to be less than or equal to. So we got is at most 0, or it's at least 2. So y is greater than or equal to 2. So we create our number line. Now, because this is using the word or, I just graph both of these inequalities separately. First, the y is less than or equal to 0. Filled in dot, going in the less than direction. Now for the 2, filled in dot, going in the greater than direction. And there, we've graphed that particular compound inequality. Now, before we go on, I want to quickly go back to one more thing back here. Notice where we have the and these words over here. Notice also that we can write it in another way by just combining them into one. Now, they still have it written in such a way that x is greater than 2, and they have it written in a way that x is less than 5. This is one way that with any inequality that you have, any compound inequality that is joined by using the word and, you can write it as a single statement. Also, keep in mind that when you see two inequalities combined in a single statement, that's this situation of using the word and our graph is going to be the intersection of those two. Okay, so now that we've looked at that, we're going to see some compound inequalities combined with and. Notice there's two inequality statements here. Here are the two that we've got. X minus 2 is greater than negative 4, and x minus 2 is less than the 3. Now, in order to solve this, there's actually two different approaches we could take. The first one is to focus in on all the sides. Now, with equations, there's always two sides, left side, right side. Notice what I've done here, though. I didn't just add a 2 to two sides because I've got more than that. I've got a left side, I've got a middle, and I've got a right side. Whatever you do in one section, you need to do in all of them. Now, if I add 2 to each section, I now get negative 2, x in the middle, 3 plus 2 is 5. So x is greater than negative 2 and x is less than 5. Graphing that, I've got my not filled in dot at negative 2. We're going in the greater than direction there, and got my dot at 5. We have to go less than, so the intersection, the area in between, would be right there. Okay, similar type equation. Now, what we're going to do this time is separate them by using the word and. Now, notice how I did that. I took this middle, and the middle part is still the same in both of those inequalities. Now, you don't have to do it this way, and you don't have to do it the first way I showed you, but you do need to pick one and find the one that really makes sense to you. Now, after I've separated them into the word and, I can solve them separately. Okay, so first I'd use my additive property of inequalities to subtract a 1 from each side. Now, because the middle was the same in both, we can basically use the same steps in both. And then I've got this negative 2x. So we're multiplying by a negative 2. I'm going to divide both sides by a negative 2. Remember what happens when you divide an inequality by a negative. You have to flip the inequality. So now we've got x is less than 2 and x is greater than or equal to negative 4. So we've got our negative 4 over there, and we would be going in the greater than direction all the way up to the x is less than 2. And so our intersection is there in between. All right, now let's solve using OR. When you're solving using OR, just treat them both as separate inequalities. We're going to solve the one on the left first, then we'll solve the one on the right. So we've got minus 5. I'll add 5 to each side of that to eliminate that minus 5. Now we've got 3y is less than negative 3, divided by 3 on both sides. So y is less than negative 1. Now that we've solved left side, we'll solve on the right. Oh, well, first let's graph it. So y is less than negative 1. There, we've graphed it. Not filled in dot at the negative 1, going to the left. On the right, we're going to use that plus 1 to eliminate the minus 1. We're going to divide by 2 to eliminate the multiplied by 2. So y is greater than 3. Now we're going to graph that one. Dot at the 3, going in the greater than direction. And because it was or, all we needed was the combination of the both, and that's what we've just made. All right, so let's look at this real-world context to it. A recommended storage temperature for chocolate is from 15 degrees Celsius to 20 degrees Celsius. Now, that's great and all, but because I've been raised here in the US, I'm not really familiar with Celsius, and I have no concept in my brain of how warm or how cold is 15 degrees Celsius and 20 degrees Celsius. So what I'm going to want to do is to write and solve a compound inequality that can represent this, all the possible storage temperatures for chocolate, and put it into Fahrenheit. Okay, so we know Celsius has to be greater than a 15 and, notice the word and less than a 20. But that's Celsius. I want to put Fahrenheit in there. Now, we're going to use this equation where Celsius equals 5/9 of the Fahrenheit minus 32. Okay, so normally we'd have our Celsius in here, but this is what Celsius is equal to. Now, if I solve for F, then I'll know what the Fahrenheit would need to be. So, in solving this out, first I've got this 5/9 right here that I want to deal with. I'm going to multiply all three sections by the 9/5, not just one section, not just where it's convenient, but all three sections. So 9 times 15 divided by 5 was 27. 9 times 5 is 45. 5 times 9 is 45. So there in the middle, we'd have 45 over 45 is just 1. Anything times 1 is itself. 9 times 20 is going to be 180. And 180 divided by 5, 36. Now, we're subtracting a 32 here in the middle. We want to get the F alone, so let's add 32 to all three sections. And we get that Fahrenheit needs to be somewhere between 59 degrees and 68 degrees. So now I've got a good concept in my brain as to how warm that is and at what temperatures and what rooms could I store the chocolate. So now let's describe a situation in which the surrounding temperature could be below the storage temperature range. We don't want to get it too cold. Then when we pull it out, it's not going to be as soft, as melty, and one in which it could be above. So places below 59 degrees, fridge, freezer, or being outside in winter, situation in which it could be above 68 degrees, outside any time past spring. Okay. Thank you. I hope this helped you. I hope this helps you work on your assignment. Good luck.